Okay, so right at the start of this unit, we talked a little bit about average rate of change, and then we looked at the way that limits can be used to find the instantaneous rate of change. We're going to be looking at a lot more right now. So here, average rate of change, remember when you see the words average rate of change, and this is for the rest of the course, you're going to be seeing those words every once in a while. And it's really important that when you see average rate of change, it has, that combination of words, that you think slope. Okay, that's slope. That's what average rate of change means. So, for instance, this question here says, find the definition of it there. It's a quantity over a period of time. The average rate of change of a quantity over a period of time is the amount of change divided by the time it takes. Okay, so for instance, if we're talking about rate of change of distance, we're talking about how far we've gone divided by how long it took us to get there. That is how you calculate the slope of distance, which is always speed. Okay, so here we have a situation where it says find the average rate of change of f of x equals x cubed minus x over the interval 1, 3. So what that means is find the slope. Okay, now slope, remember, is just, change in its rise over run, if you want to think of it that way. A rise over run. Oops. Rise over run, which is also the same as delta y over delta x. That means change in y over change in x. And really what that's equal to is f of b minus f of a over b minus a. Or f of a minus f of b over a minus b. It doesn't matter as long as you're consistent. So when we say f of b, what does that mean? Okay. Now, AB in this case, AB, just so to be clear, AB is 1, 3. It's those two interval points. Those are x points. Those are x values. So they're my A and my B. So what I'm actually mean when I say FB over minus F of A, I mean F of 3 minus F of 1 over 3 minus 1. And that's what I'm talking about here. Okay, so f of 3, you can either do it right on the work if you wanted to, or you could do it off on the side if you so chose. Okay, so I'll just do it right in the middle here. But you could do it like off on the side. You could be like f of 3 equals and like calculate it out. But I'll just do it inside here. F of 3, if I plug 3 in, I'll get 3 cubed minus 3. Take away, because it's minus f of 1, 1 cubed minus 1. Over 3 minus 1. Okay. Now I can start doing some of that math. That's 27. 3 cubed is 27. Minus 3 is 24. Minus 0. So the top is just 24. And the bottom is just 2. So pretty straightforward. My average rate of change is 12. Okay, that's the average rate of change of that graph between the values of 1 and 3. So what that means is if I look at that graph, and I don't know exactly what that graph looks like, but it's a cubic, so it probably, it would be x and x squared minus 1, so it would probably look something like that. Okay, it'll look something like that. Now, if we had that graph, what it's saying is that the average rate of change between the values of 1 and let's say, so this would be 1 on the x-axis, so like that's 1. And let's say this is 3. They're saying the average rate of change, so if I just drew a straight line between those, nice straight line between them, the slope of that line would be 12. Okay, that's what that's saying. Okay, so let's look a little bit further at that. Okay, so here's an example of a similar situation, but it's like a more of a real life application problem, I guess, if you could call it that. This is some data from growing fruit flies in a lab. So they're saying use the points P 23,150 and Q 45,340 to compute the average rate of change of the slope of the secant line PQ. Okay, so secant line really just means a line that connects 2 points on a graph. That's what a secant line is. So it connects 2 points on a graph. So we have it connecting P and Q here, and it just wants us to find the average rate of change. So it's just like the drawing I just drew you. It just wants the slope here. So this is just a simple graph where it says, after 23 days, we have 150 fruit flies. After 45 days, we have 340. So if we were trying to find the average rate of change here, we would just be doing 340, take away 150, over 45, minus 23, because I'm just doing slope. Like, really don't overthink this, guys. That would be 190 over 22, which is also 95 over 11. Okay. Now, what would the units for this be? And I don't know what the decimal is because I don't actually have a calculator on me, which isn't a good idea. I might need to grab one later. But 95 over 11-ish. Now, the units here, and this is actually really important in this course, is understanding what the units are. Slope, remember, slope is always rise over run. So your units are always, so I'll just write this here. The units are always the y units over the x units. It makes sense, right? So here, it's number of flies per day, because those are the two units. Number of flies on the x-axis, or on the y-axis, sorry, the y-axis, and days on the x-axis. So we have number of flies per day. So whatever 95 over 11 is, pretty close to 9, about 9 flies per day. That's how you would answer that question, just average rate of change. When you see the word secant line, it's a word you're going to be seeing all the time. People are going to be asking me, what is a secant line? Because some people don't pay attention, Sebastian. Secant line is a line that connects 2 points on a graph. Okay, so this is where limits are. We get into why we've been learning limits, and we get into kind of starting to get further into calculus, what calculus is really about. Using secant lines, we can approximate the rate at which the fruit fly population was growing on the 23rd day. This can be done as follows, and there's something really fun to read here. So I'm just going to read it, and then I'll try to explain it to you. As Q approaches P along the curve, the secant line PQ approaches AB. The tangent line, which was drawn by I at point P. Now remember, a tangent line, just to take a little break, a tangent line is a line that only touches the graph once. It it can touch it again later, but it's more like this idea that we're just grazing that point P. So point P, it's just like the line is just barely touching it. We talked about tangent lines in grade 9 when you looked at circles. So a tangent line is a line that just like barely grazes our thing. It just touches it right at that perfect point. The average rate of growth rates for increasingly smaller time intervals approach the slope of the tangent to the curve at P, 17.5 flies per day. This slope represents the rate at which the fly population was growing on day 23. That sounds really complicated, but it's not that complicated. All they're saying is that if we start, at P and Q, so we start with the line between P and Q here, that line, is not super close to what's happening at P, because at P, the graph is much steeper, because that graph looks sort of like this, right? And P is like right here. So it's where the graph is quite steep, but that secant line isn't steep. Now, the closer we bring that point Q, or whatever, we bring the point that we're looking at the secant line, like if I bring it a little bit closer, I get a slightly steeper line, and that slightly steeper line is closer to being what is happening at P. And if I get even closer yet, I keep getting closer and closer and closer until I'm like right here. And that line there, okay, that line that's like, even AB is pretty dang close to just looking like the tangent to P. So the tangent line to P, like if I was like on this one up here that I drew, if I was trying to draw the tangent line, it would be like line that just like perfectly kind of grazes the graph there. Okay, that just sort of, is like sort of like if that line was straightened out right there, if that curve was straightened out right there, it's what it would look like. And that slope, the slope of this line, is an approximation of what the instantaneous rate of change should be. So what would the rate of change be on that day? And that's kind of what we're looking at here, and what a lot of calculus is about, is figuring out how quickly are things changing right now, or how quickly will they be changing in a week, or how quickly are things changing in general. So all these questions about change, that's what we're looking at in calculus. So hopefully that kind of makes sense. So it's all about this secant line getting closer and closer and closer to the tangent line. The tangent line is the line that just perfectly grazes our. Okay, so this is a little bit about that thing, the tangent. The word tangent is derived from the Latin word tangens. I'm sure you're all very interested in that. It means touching. Okay, so in general, if a curve has an equation y equals f of x, and we want to find a tangent to the curve at a point P, A, f of a, so that, just to be clear, a is the x value, f of a is the y value, then we consider a nearby point Q, x, f of x, and compute the slope of the secant line PQ. So it's like we pick a point just close to P, make a secant line, and we look at that slope. Okay? Then we let Q approach P along the curve by letting X approach A. So what that means is that we're bringing that other point closer and closer and closer to P. We're bringing the A and the X, which are the two X values, we're bringing them closer together so that these 2 points are getting really close together, like arbitrarily close together. So close together that they're basically on top of each other. And when we have that and we draw the secant line between them, it's going to really closely approximate that tangent line, which is always what we want to find, because that tangent line represents the rate of change right now, that instantaneous rate of change. So there's 2 different formulas for this, okay? And they're both limit formulas, because what we're doing is we're letting that x value approach that a value. So there's different ways to look at it. The first one, and we mostly will use the second one. I know it looks more complicated, but it's more easily used actually, believe it or not. But anyway, so this first one, f of x minus f of a of x over a, over x minus a, where the limit of x is approaching a. So that's where we're saying x and a are getting closer together. Now the second one is actually, I think, a more important formula. And just to be clear, MP of Q means slope of PQ. Okay, we're saying slope of that secant line. Okay, so the second formula for the same thing is f of a plus h minus f of a over h, where h is approaching 0. Now this one is a little bit different, but I want to explain it to you, and hopefully it makes sense. So we're talking about our value a. So remember P. Okay, the x value of P is a. So we're talking about that value a where we want our tangent line. Okay, we want to figure out what is the tangent line at a. Okay, so imagine I have a graph. Okay, and I have a graph like this, and here is my a value. Okay, now what this means is h is actually the distance between a and whatever other value we're picking for q. So say I tell you, okay, that q, our value, the point q, this is point P that I've already drawn, that's point P. Okay, say I tell you that point q is just a little ways down, like right here. Okay, it's getting closer all the time. We're always trying to get it closer. Okay, that's value q. Then what h is h is the horizontal distance between them. That's h. Okay, so obviously then, if that's h, if this point here is a, right, if that value is a, and that other line I drew is h up, that other line would be a plus h. I feel like that kind of makes sense. Okay, I hope it does. Right, like if I told you that a was 3 and h was 2, then you're like, well, it's 2 higher than 3, so it'd be 5. Okay, I hope that kind of makes sense. It's a plus h, and what we're saying is that we're going to let h get closer to 0. which means that we are closing that space in between the 2 points. Okay, we're closing H so that it's getting smaller and smaller and smaller, and eventually P and Q are just going to be on top of each other. That we use all the time. Now the exact same thing is happening in the other question, in the other formula rather. It's just that the terminology is a little different. So we're still having our graph. We still have P with A, but now we have Q with X. And all they're saying is they're letting X get closer to A. Okay, that's what limit of X approaches A means. So it's the exact same concept, it's just written out a little bit differently. So hopefully that sort of makes sense. If not, well, you've got some time for me to explain it to you again, but you need to understand it. This is a really important concept. So it's all about bringing these 2 points closer and closer together. Now let's just try using the formula. Okay, so it tells us to use formula 1 and formula 2. Okay, to write an equation for the tangent to the parabola at this point. Okay, so they gave us the point, and they gave us the equation, x squared. It's a pretty simple equation. So here, okay, my slope, MP of Q, if I'm using this formula, limit of x approaches A. So in this case, A, what's A again in the question? Does anyone remember, hopefully? Okay, let's just see. So A is the x value of the point we're looking at. So in this case, it is 3. Okay, so 3. And now it's f of x minus f of a. So f of x just means the equation, so x squared in this case. Now f of a means a filled into the equation. So in this case, our a value is 3. So I could write f of 3 if I wanted to kind of take it a little slower, but I know it's going to be f of 3, so it's going to be 3 squared, which is 9. So it's minus 9. Okay, if you wanted to write 3 squared, you could write 3 squared. Now on the bottom, it's x minus a, which is x minus 3. Okay, now this is just a limit, so we just have to factor. You know, if I plugged 3 in there, I'd get 0 over 0. So I factor the top, I get x plus 3, x minus 3 over x minus 3. I cross off the two x minus 3's. And what do I do to get my answer? I plug in 3. So I get 3 plus 3 is 6. So my slope is 6. Okay, now on this question, and people aren't going to like this because it looks harder, but and to be honest, in this situation, it is harder. But the reason that this formula is better, or I don't want to say better, it's going to be more widely used for us, is because it actually allows us to solve this even when we're not given a point. But for now, in this situation, like I admit that the one on the left is easier for this particular situation. But you're going to find that this formula gets used more often. This formula is called the difference quotient, and you're definitely going to have to do it on the exam. So please don't try to like only use the one on the left. You're going to have to do this one on the right. So, but I'll show you how to do it. It's not that bad, but it's a little different. So A is still 3. But h is not anything. I can't plug something in for that. So when it says f of a plus h, it means 3 plus h, and that's what's going in for x. So instead of x squared, it's going to be 3 plus h squared. Minus f of a, which is the same thing as before. Remember, f of a is f of 3, so that's 3 squared, which is 9, over h. And this, I hope, looks very familiar to you because we've done some like this already. That's because this is such a common equation that we're going to be using that I made you learn how to do it. So this is going to be 9 plus 6h plus h squared minus 9 over h. So what happens is the 9's cancel off, and I can factor out an h. So it's h times 6 plus h over h, so the h's can cancel off, and I plug in 0, so I get 6. Okay, so obviously a little harder than the one on the left. There's a little more expansion and stuff, but seriously, you're going to be using the one on the right more often, I promise. So get used to it. Now, the actual question here was not find the slope. It was write an equation for the tangent to the parabola at this point. So we have our slope. We know the slope is 6. And we know our point is 3, 9. Okay, that's the point. That's what it says up there, right? Yeah, 3, 9. So the equation that we can write for that, we should be going back to what we did in pre-calculus. You should be using this form. Oh, this isn't the form you learned, sorry. Mx minus x1 plus y1, like that. Okay, so here that is 6x minus 3 plus 9. Okay, and that is your equation. Okay, so that equation, just to be clear about what we have actually found here, because I'm sure there's people who don't know or aren't sure. What we've actually found is if I graph y equals x squared, okay, it looks like this, right? Okay, and let's say this is 3. Okay, so this is 9, right? Okay, what we found is if we drew the tangent line there, like if I drew it just barely grazing that point 3, okay, that 6 is the slope of that line. And this equation is the equation of that line. Okay, so this line would match with that equation. That's what I found. And what that is, I know that in this context doesn't seem like it means anything because I'm just talking about a random equation. But imagine if this graph was about something, it was a context, this would tell me the rate of change of whatever that context is at this exact time. Okay, that's what we're really getting into and what is one of the founding principles of calculus. Okay, so just to look at that whole equation, whole part again. Okay, that's what we're looking at here. Okay, so you have the two different ways to compute the limit. You get the limit, that's your m value. Then we use our point and we plug it into that point slope formula that we learned a long time ago, but also just recently in pre-calculus. So this is how you do this kind of question. Okay, you're going to be doing a ton of these, so get ready. Okay, let's just look at it one more time. We're going to do just formula A here. Okay, so this is the first formula, and it just wants the slope. It doesn't want the equation this time, so we don't have to do an equation after. So we're just going to do this formula. So limit as x approaches, what would be my A value here? So the A value, again, people for some reason get mixed up about this. The A value is always the x value of the point that you are trying to find the tangent at. So we're trying to find our tangent at 217, so A is 2. Okay, so it's f of x minus f of 2 over x minus 2. Now notice that this formula is literally just the slope formula, by the way, right? This is the slope formula for between x, x and a. Like that's what this is. Just I don't think I mentioned it earlier and maybe people didn't notice, but this formula is just the slope formula. Up top, it's the difference between the y values, and on the bottom, it's the difference between the x values. Okay, that's it. So just so that you realize. Okay, so our x is approaching 2. F of x is just f of x, so it's 3x squared plus 5, minus f of a, which is f of 2. So I plug 2 into there, and I could, you can write it out, or you can do it in your head, or whatever you want to do, but just be really careful, please, over x minus 2. So on top there, if you're doing it this way, what I need you to do is be really, really careful. So the 3x squared plus 5, you can lose the brackets because there's nothing going on there that really requires them. But what's really important is that you don't forget about the brackets here and here. Because that subtraction sign does apply to both of the things inside those brackets. So depending on how you do it, that you could make a mistake. Now, personally, what I would probably do is actually compute the number in there. So that's 3 times 4 is 12, plus 5 is 17. So this is actually just minus 17 over x minus 2. So if I type that into my calc, or, do my little adding thing there, I get 3x squared minus 12 over x minus 2. Now this is definitely going to be factorable. It's always going to be factorable. You're always going to be able to cancel something. So this is limit x approaches 2 of 3. I would even maybe factor off on the side or something. Like that's 3x squared minus 4, which is 3x minus 2x plus 2. Just to try to keep my work from like getting exceptionally long, but try your best, over x minus 2, and the x minus 2's cancel, and then I plug the 2 in, so I get 3 times 2 plus 2, which is 12. So my slope is 12. Okay, winner. Okay, the slope is 12. So I use that slope formula, okay, and I let my x value get closer to my a value, or my x value get closer to my a value, and I found the point. Okay, this is yet again means I found the tangent line going through that graph at that point. Okay, so that's quite steep. 12 is quite a steep slope. Okay, so we're going to use now the second formula again, and you're going to see how fun it is. This one's going to be really bad. Get ready. Okay, so write this one down, please, even if you don't want to write anything down. So some of you guys at the back table, you should write this one down. I cannot be clear enough about that. You're going to need this example at some point probably to look at. And again, this is the slope formula. Okay, so what we're looking at here is and this one doesn't look like the slope formula, but let's just talk about how it's the slope formula. You don't need to write this part down necessarily. It's more for your understanding. So if I graph x cubed minus 5x plus 5, I don't know what it looks like, so it's not going to be helpful, but it's a cubic, so I'm going to just say it looks something like that. Okay, and let's say the value 2 is right here. Okay, so what that point is A, right? That's A. Okay, so A plus H would be somewhere like over here. That's A plus H. So the point is somewhere up there, and we're talking about the line between them. So here, that the top part makes sense because it's the y value subtracted, right? So it's f of A plus H, which would be the y value minus f of a, which is that y value. The top part looks kind of right because the top part of slope is that y2 minus y1, and that's what we're looking at there. Now the bottom is because the x values are subtracting. So what it is it's we have f of a plus h is the higher y value, take away the lower y value, which is f of a, and then on the bottom, what we'd have is a plus h minus a, because it's always the x's, right? And these are the x's. So a plus h minus a, and then the a's cancel, leaving just the h. That's where this formula comes from. But that formula is just slope, just the same way that the other formula is just slope. Okay, sorry, I was trying to get rid of that picture, but I guess I can't. Fun. Okay, so at x equals 2, we want to find this limit. So if I start doing this, it's going to be a long one, guys, as I said. So it's long, and I know it's long because of the a plus h. So remember that means 2 plus h, but here what that means is that 2 plus h goes into each of these x's. So it's 2 plus h cubed minus 5, 2 plus h plus 5 minus, okay, so that's f of a plus h, and then f of a is that with 2 plugged in, right? So it's 2 cubed minus 5 times 2 plus 5. Sorry, this is why I was trying to erase that, but I could not do it because of the angry program, over h. So that top part is really long, okay? And that's why this is such a long thing. And even, to be honest with you, I would probably do, like I did my factoring out separately before, I would probably do my 2 plus h cubed out separately somewhere. If it was me, I would do something like this. I would go off on the side, and I'd be like, 2 plus h cubed means 2 plus h times 2 plus h. Oh my god. Oh, sorry. Times 2 plus h, which is 4 plus 4h plus h squared times 2 plus h. It is not, by the way, if you just thought, oh, I could just do 8 plus h cubed, you are totally wrong. Look at all this work. Okay, so that's going to be 8 plus 4h. I'll just do it all the way out. There are like slightly faster ways to do this, but unless you are like feeling like super confident, please maybe just do it all the way out. Okay, and I get finally h cubed plus 6h squared plus 12h plus 8. Okay, brutal. Okay, so h cubed plus 6h squared plus 12h plus 8 is what I get. So that's just that first part. Okay, believe it or not. I know it's crazy. Okay, I'm just going to erase some of this. Okay, so here what I have is I have the limit of h approaches 0 of, and at the top there I have h cubed plus, what was it again? 6h squared, yep, 6h squared plus 12h plus 8 minus, and I would do this, so minus 10 minus 5h plus 5 minus, and I would do this part probably. So that's 8 minus 10, which is, so because 2 cubed is 8, minus 5 times 2 is 10, so 8 minus 10 is negative 2, plus 5 is 3, so it's minus 3. And I know that looks crazy, but a magical thing always happens at this point. Okay? So the magical thing that happens is that things always cancel off as long as you've done it correctly. So as long as you haven't done anything too crazy, this will just work out nicely. So here, my limit as h approaches 0, I have h cubed, I have 6h squared, I have 12h minus 5h, which is 7h. I have 8 minus 10, which is negative 2, plus 5, which is 3, minus 3. So those 3's cancel. Now, at this point, all the time, like I said, all the time, everything should cancel except your terms with h. Okay, like all the numbers without h's should cancel. So I'm left with h times h squared plus 6h plus 7 over h. And the h's cancel off. And then I plug 0 in for h, and I get 7. So my slope here was 7. That's how this works. Okay? So, I know that was really fun. Okay, and I hope you see what I mean, that it's quite a lot of work. You will have to do questions like this. This is not like, this is not a crazy one. It is not like a question that's beyond what I expect of you. I would expect you to be able to expand cubics. So please practice them. I'm going to have the sub hand out a worksheet right now, and it's really important that you actually give it a try. Okay, I will see you guys tonight at night class. If you decide to come, I suggest you do, because you should be practicing this. This is like a skill you need to practice. So come and give it a try, and I can teach more about limits and how secant lines approach each other if there's some confusion, which I'm sure there will be, because it is complicated at first. So yeah, that's everything. Okay, I'll see you guys tonight.